Welcome. We are going to solve an example called undamped oscillation of a rolling hoop. That's right. The hoop is something you can say like a hollow cylinder or like this. A hollow cylinder. I'm going to consider it thin-walled hollow cylinder. And the problem says that a small ball is attached to the inner surface of a thin-walled hoop. Okay, the mass of the hoop is capital M and the mass of the ball is this. Their masses are comparable. And the radius of the hoop is capital R. The hoop can roll along a horizontal surface without slipping. Pure rolling. This is a case of pure rolling. What is the period of oscillation of the hoop about the equilibrium position in the case of a small amplitudes? That means we need to find out the time period of a small oscillations of the hoop. The acceleration due to gravity is g. Of course, these things are fine. But in equilibrium, the hoop must be here. The hoop must be in here. And now it has displaced some by some angle, say alpha. And if this length, the point of contact, has moved the distance x, so will be done by the center of the hoop. That will be a distance x as well. This is the most basic idea behind the pure rolling. And the speed of the center of the hoop, if I would like to write it v should be equal to dx by dt. So this all comes from the pure rolling. And you can see one more thing, that if we consider the change in potential energy of the hoop with the ball, you can see here there is no change in the gravitational potential energy of the hoop. Only the gravitational potential energy of the ball has been changed, and so that the ball has come up with a distance this distance. And since this length can be written simply as r cos alpha, so this length is r minus r cos alpha. So the change in gravitational potential energy of the hoop plus ball can be simply written as mg r1 minus cos alpha. And this alpha can be written as x by r for whatever be the value of x. Alpha is always this. So change in potential energy is something like mgr 1 minus cos x upon r. This is 1 minus cos theta. And we have to consider that this alpha is quite small. So to do this, I would like 1 minus cos alpha. If I made the assumption that alpha is so small that I can assume alpha equal to 0, then everything goes, nothing will happen. So I have to make the approximation to the second order. So I should write 1 minus cos alpha equal to 2 sine square alpha by 2. And that means if alpha is very small, that will be approximately 2 alpha square by 4. That means I should write it alpha square by 2. And since alpha is, and this alpha square by 2 is equal to x square by 2r square. X square by 2r square, because alpha is x by r. So the change in potential energy, I would like to finish it first. That will be mgr x square by 2r square, and that is equal to mg x square by 2r. So this is the change in potential energy of the hoop and the ball. And now I would like to write the kinetic energy of the hoop and the ball. So I am going to look for kinetic energy of the hoop first. Kinetic energy of the hoop is obviously half mv square, capital M capital V square. what about the kinetic energy of the ball? So I'm going to make the picture like this, so that the hoop right now is, the ball right now is here, and this angle is alpha, and this is the hoop center that is moving with velocity v in this direction. So if I place an observer here, the velocity of this ball will be in this direction. For this observer, it will see it only rotating or moving in a circular path with angular velocity omega, and that omega will be equal to v upon r, as we all know from the pure rolling. So basically for this observer, its velocity is also v, and this angle is alpha, because this angle is alpha. So the perpendicular to this and perpendicular to this, the angle between them will also be equal to alpha, so that I can write the components of this velocity v as v cos alpha, and this one is v sin alpha. And that means the velocity of the ball at this moment can be have a horizontal component v cos alpha and vertical component v sin alpha with respect to the observer moving towards right with velocity v. So its velocity of the ball with respect to ground, we need to add one more thing, that is the velocity of its observer sitting in the center of the hoop. So finally the velocity of the ball becomes, so have two components. This component is v multiplied by 1 minus cos alpha, and this component is v sin alpha. Okay, so what is its velocity? In fact, its velocity can be written as v square 1 minus cos alpha square plus v square sin square alpha. This is the velocity of the ball at this moment, and in the next step I would like to write in it like this. V square was taken out of the square root sign, and then I can write this will be 1 minus cos square alpha plus sin square alpha. Yeah, that's correct. And that means 1 plus cos square alpha minus 2 cos alpha plus sin square alpha, and that means it becomes 1 plus 1, 2 minus 2 cos alpha. And this is not a square, basically this is simply b. This is simply b. I started writing down a square and it becomes a square like this. This is v, so I should write this will become root 2b under root 1 minus cos alpha, and I earlier obtained the value of 1 minus cos alpha. What was it? I missed out. Yeah, the 1 minus cos alpha value is this, x square by 2r square. So its value becomes root 2v x square under root x square by 2r square. X square by 2r square. And since x is much less than r, this is the requirement of the problem. So this term becomes 0. That means velocity of the ball is very small compared to the velocity of the hoop, and the kinetic energy of the ball can be neglected. That's right. That should happen in this problem. And then kinetic energy of the rolling hoop consists of kinetic energy of the translational motion and the kinetic energy of its rotational motion, and both will be equal to same in the cases of ring or hollow cylinder. We knew the kinetic energy of translational motion and kinetic energy of rotational motion, they are always same. So the kinetic energy of the hoop can be simply written as half mv square plus half mv square, and this finally becomes mv square. And now I am going to use the conservation of mechanical energy, that I am going to equate the potential energy and kinetic energy, and or I can write its total mechanical energy is equal to sum of kinetic energy plus potential energy, and its kinetic energy is only half mv square plus potential energy was something like mg x square by 2r. So I'm going to write it down. It was mg x square upon 2r, and this total mechanical energy is a constant. So if I differentiate with respect to time, I can write here m2v dv upon dt plus mg by 2r 2x dx upon dt, that will be equal to 0. And this v thing got out, so that I have the equation something like dv by dt plus mg upon 2mr x, that is equal to 0. And you can see from here that the angular frequency of this small oscillation will be simply under root mg upon 2mr, and that means time period of the motion is 2 pi upon omega, that means 2 pi 2mr by mg, and that will be the answer of this problem. We solved it. But I would like to make a comment here. You must note that the given solution is completely inapplicable when m tends to 0, because the expression we obtained for the period gives t tends to 0 in this case, and which is incorrect. It can be shown that with this with a weightless hoop, any oscillation of the system, even arbitrarily small ones, are not harmonic, and their period depends on the amplitude. So, and one more thing, when solving such a problem, it is already necessary to take into account the kinetic energy of the ball, and which we neglected because it was following the conditions of the problem. So I did it. Thank you very much for watching.